Welcome to the second lecture of module 4. In this module, we are discussing reactor design. Before going to this lecture, let us have brief recap on our previous lecture. In lecture 1, we considered introduction to reactor design, and we have considered what are the requirement to design a particular reactors, and then we have considered the concept of decoupling of mass and energy balance equations, and which with relevant examples of exothermic, highly exothermic combustion reactions of methane in presence of oxygen. And then we have considered general mole balance equation, and taking into consideration this general mole balance equations, we have tried to design ideal batch reactor, and then we have seen what are the difference between the space time and the batch reactor time. So, we have discussed also space time and space velocity in lecture 1. Space time and space velocity, these are natural measures for the flow reactors, whereas the time t in case of batch reactor is the natural measure for the performance of the batch reactor. In this lecture, we will mostly concentrate on the design of ideal CSTR. CSTR means continuous start tank reactor, or it is a mixed flow reactor. So, this is flow reactor, it is used in different nomenclature in different books. We can call it continuous start tank reactor, or as well as we can call it mixed flow reactor. As we have said that for batch reactor, we use only for the specialized applications when the quantity of the material to be processed is less, or where we need to test new products. So, there we can use batch reactor, or in a case where the product or the reactant during the course of the reactions create scaling of the reactor, in which we need to frequently clean the reactor. In that case, batch reactor is preferable, whereas for large scale industrial production, usually we use the flow reactor. One of the flow reactor is CSTR, continuous start tank reactor, and another reactor is the plug flow reactor. So, in this we will consider mostly ideal CSTR design. So, the lecture outline is we will discuss ideal continuous start tank reactor design, and we will see few examples to see how to calculate the different parameters for the continuous start tank reactor. So, let us consider ideal CSTR. It is a tank fitted with impeller. So, this is impeller, and this is the inlet of the reactant, and this is the product output. Now, we know the general mole balance equation, say F J naught minus F j plus integral over volume R j dV is equal to dNj dt. Now, if we consider steady state, so at steady state what will happen? The change of mole with respect to time will be 0. That means, here instead of dt we can write d tau for the flow reactor. So, at steady state we can write dNj d tau is equal to 0, and if there is no special variation. So, for the case of no special variation, that means it will not change in position. So, in that case this integral term we can write integral Rj dV V would be equal to Rj V. So, this is the case of for continuous start tank reactor, the reactant mixture is very well mixed in this region and they are homogeneous. So, there will not be any special variation of rate over this volume. Then the overall mole balance equation or general mole balance equation, that is Fj naught minus Fj plus integral V Rj dV is equal to dNj d tau. So, this is 0. So, we can write F j naught minus F j plus V R j is equal to 0, and if we rearrange we will get V is equal to F j naught minus F j divided by R j. Now, if we write this equation for a particular species, say for reactant A, we can write V is equal to F A naught minus F A divided by, this is minus R j. So, divided by minus R A. Now, if we substitute here F A naught minus F A would be F A naught minus F A naught x A. So, it will be plus F A naught x A divided by minus R A. So, this would be equal to F A naught x A divided by minus R A. As we know, F A is equal to F A naught into 1 minus x A. So, from here we can write V by F A naught would be equal to X A by minus R A. So, now if we rearrange this equation, then we can write V by F A naught would be equal to tau by C A naught, which is equal to d x A divided by minus R A, which is equal to x A by minus R A, or in other words we can write tau is equal to 1 by S, which is equal to V by V naught. We have done before the relations between the space time and space velocity would be equal to V into C A naught divided by F A naught, which is equal to C A naught x A divided by minus R A. So, this relation after the rearrangement is valid for any epsilon A, and where x A and R A measured at the exit condition, these are the same condition within the reactor. As you know, for perfectly mixed flow reactor there is no special variation of the concentration. So, the concentration which we measure at the exit conditions should be same at the inside the reactor at any location at any time. Now, if we generalize this relation and if we consider fit on which the conversion is based is entering conditions is represented with 0, that means the fit on which conversion is based if we represent with subscript 0, enter the reactor partially converted. Then we represent with I, and living conditions of the reactor is represented by F. So, entering conditions, if it is partially converted, which was represented with 0 earlier, is represented by I, and the leaving conditions of the reactor, which is the final, is represented with F. Then the earlier equations we can write V by F A naught would be equal to delta X A by minus R A F, which is equal to X A F minus X A I divided by minus R A F, and or tau is equal to V C A naught by F A naught is equal to C A naught into X A F minus X A I divided by minus R A F. Now, if we consider special case for constant density system. So, if it is constant density system, that means epsilon A is equal to 0. So, the conversion can be related X A is equal to 1 minus C A by C A naught. Then we can write V by F A naught would be equal to X A by minus R A, which is equal to C A naught minus C A divided by C A naught minus R A. So, if we substitute X A from here, which is C A naught minus C A by C A naught. So, if we substitute X A from here in this, so we will have this relation, or we can write tau is equal to V by volumetric flow rate, which is equal to C A naught X A divided by minus R A, which from here we can write it would be equal to C A naught minus C A divided by minus R A. So, this is for the special case of constant density system. Now, if we consider first order reaction and it is for constant density system, then we can take first order example. The rate would be minus R A is equal to K into C A. Now, tau would be equal to C A naught X A by minus R A. So, if we substitute, this would be equal to C A naught X A divided by K C A, which is equal to C A naught X A divided by K into C A naught into 1 minus X A. So, this C A naught, this would cancel out and we will have X A divided by K into 1 minus X A. So, this can also be written as Ca naught minus Ca divided by K into Ca. So, now we can write K tau from here. K tau would be equal to X A divided by 1 minus X A, or which is equal to Ca naught minus Ca divided by Ca. So, this is for the first order constant density system. Now, if we consider second order constant density system, it would be minus R A is equal to K into C A square, and epsilon A is equal to 0, constant density system. So, the K tau equations for the second order reactions would be equal to Ca naught minus Ca divided by Ca square. So, from here we can write Ca would be equal to minus 1 plus root over 1 plus 4 K tau Ca naught divided by twice K tau. So, this is only taken the positive part, as you know the concentration can never be negative. Now, if we consider first order reactions and variable volume system, in that case we can write there is linear relation between the volume and the conversions. So, linear relation in the volume of the reactor and the conversion. So, we can write V is equal to V naught into 1 plus epsilon A x A, or Ca by Ca naught is equal to 1 minus x A divided by 1 plus epsilon A x A. Now, the equations for K tau would be equal to x A into 1 plus epsilon A x A divided by 1 minus x A. So, this is relation for first order variable volume system is valid for any epsilon. Now, let us take an example how to calculate the parameters for the continuous star tank reactor design. A gaseous feed of pure A 1 mole per liter enters a mixed flow reactor having volume 2 liters and reacts as follows. So, this is the reactions twice A2 R, where a rate of reactions is given minus R A is equal to 0.05 C A square mole per liter second. So, this is second order reactions from the rate equations which is given, and we need to find out what feed rate, that is in liter per minute, will give an outlet concentration, that is C A is 0.5 mole per liter. So, it started with pure A and we have the exit concentration which is given 0.5 mole per liter. So, we have to find out the feed rate required for a start tank or mixed flow reactor. So, let us solve it. If we evaluate the term, first thing we have to do is the evaluation of the epsilon, that is the change in volume, that is fractional change, that is epsilon A would be equal to 1 minus 2 divided by 2. So, as we can see from the stoichiometry, 2 moles of A reacts to produce 1 mole of R. So, 1 minus 2 divided by 2. So, this is equal to minus 0.5. Now, as it is second order reactions, we know the relations between the conversion and the concentration. So, X A is equal to C A naught minus C A divided by C A naught plus epsilon A X A. Now, if we put the values, that is C A naught is given 1 mole per liter, C A is given 0.5 mole per liter, and epsilon A is evaluated here. So, if we put over here, this would be 1 minus 0.5 divided by 1 plus minus 0.5 into 0.5, this is C A into 0.5. So, this would be equal to 2/3, 2 by 3. So, we have calculated X A, and now if we use the design equation for the CSTR, we can write the volumetric flow rate or the feed rate V would be V into capital V volume into minus R A divided by C A naught into X A. Now, if we substitute the rate equations which is given over here, which is equal to V into 0.05 C A square divided by C A naught into X A. Now, if we substitute the values, the volume is given 2 liter volume. So, the reactor volume is 2 liters. So, 2 into 0.05 into 0.5 square, since C A is equal to 0.5, which is given mole per liter, divided by C A naught initially 1 mole per liter. So, 1 into the X A which we have calculated which is 2/3. So, this would be 2/3. So, if we calculate, the volumetric flow rate would be 2.25 liter per minute. Let us take another example to calculate the kinetics of the reactions in a CSTR. A pure gas A at about 3 atmosphere and 30 degree centigrade, 120 millimole per liter is the feed rate, is fed into a 1 liter mixed flow reactor at various flow rates. There it decomposes and the exit concentration of A is measured for each flow rate. From the following data, which is given over here, the volumetric flow rate and the concentration. So, different volumetric flow rates are given. From the following data, find a rate equation to represent the kinetics of the decomposition of A. Assume that the reactant A alone affects the rate. So, the decomposition reactions is given A to 3R, and it is said that reactant A alone affects the rate of reactions. This is the problem. Now, let us solve it. So, this is a continuous start tank reactor. So, concentration of A Ca naught, the initial concentration is given Ca naught 120 millimole per liter, this is the concentration. So, 120 millimole per liter, condition 3 atmosphere, 30 degree centigrade at various volumetric flow rate B naught. Volume of the reactor which is given 1 liter mixed flow reactor. So, this is 1 liter and concentration coming out is various Ca. Now, the reactions which is taking place, that is A to 3R. For this we can calculate the change in volume, this is gas phase reaction. So, epsilon A we can calculate. So, 3 minus 1 divided by 1, which is equal to 2. So, now for each run we need to calculate the rate minus Ra. As we know, for the reactions given, we can write minus Ra would be equal to Ca naught into Xa into V naught by V. So, which we can write Ca naught into Ca naught minus Ca into V divided by Ca naught plus epsilon A Ca into V. So, if we substitute the values, so minus Ra would be equal to Ca naught is 120. So, it is 120 into 120 minus Ca into V naught divided by 120 plus epsilon A we have evaluated, which is 2. So, 2 into Ca into volume of the reactor V is given 1. So, for each run we can calculate based on these data volumetric flow rate. For each volumetric flow rate we have concentration Ca, at different volumetric flow rate. So, we can calculate, substitute volumetric flow rate and concentration and calculate rate. So, now we can evaluate the rate at every conditions. So, this is for the volumetric flow rate of this one and this one. So, we can calculate, if we substitute these two over here, and we can get minus R A is 3.6, and hence for every condition we can calculate the values of minus R A. Now, if we consider nth order reaction with respect to A, consider nth order reaction with respect to A. As it is said, only reactant A alone affects the rate. So, we can write minus R A would be equal to K C A to the power n. Now, if we take log of this both sides, it will be ln minus R A is equal to ln K plus n into ln C A. So, now we can calculate the data. So, we have calculated different R A values and we know the concentration. So, we can calculate the term ln minus R A. So, if we take from these data points, so we can calculate ln terms, ln minus R A, and since we know for each rate we know the concentration. So, we can calculate ln C A. So, in this equation we can calculate this part and we have calculated this part. Now, if we plot these values ln minus R A versus ln C A. So, this is ln minus R A and this is ln C A. So, this will give a straight line with a slope of that equation minus ln minus R A is equal to ln K plus n ln C A. So, the slope of this curve is n. So, the slope can be calculated here, the slope n is equal to 2. Now, we can either calculate the intercept which is ln K as per the equation, or we can substitute in the any rate equation for any data points. So, we can write, if we consider this first data point 1.281 and 3.401. So, 1.281 is equal to ln K plus 2 into 3.401 if we put from here, we can calculate K is equal to 0.004. So, once we calculate K, or the same thing we can calculate, extrapolate this, and we can calculate from the intercept. So, the rate equation should be minus R A is equal to 0.004 C S square, which in millimole per liter minute. So, this way we can find out the rate equations for a particular reactor data. Thank you for attending this lecture, and we will continue our discussion of reactor design in the next lecture, and in the next lecture we will mostly consider design of the ideal flux flow reactor.